I'm going to explain another aspect of T distribution, and probably you have you have watched my videos which I uploaded yesterday, where I discussed about T statistic on the basis of 2 samples and 1 sample, and also I discussed about paired T test. Right now I'm going to discuss T test for testing the significance of an observed sample correlation. So this is the thing that I'm going to discuss today. Correlation, you already know that if we have a bivariate distribution, we can find the correlation coefficient between the two. Now, this is not only the case with the bivariate distribution. Even if the case is multivariate, we can calculate correlations like multiple correlation, partial correlation, which hasn't been discussed in the class because it is beyond the scope of the syllabus. Anyways, for multivariate distribution, we can study the correlation coefficient between the concerned variables. Now, when the testing of correlation comes, then the question of testing comes, then it is quite obvious that we want to test the population. So since we are actually collecting the sample from the population, the two variables, the two random variables that are associated with the population, they must be somehow correlated with one another or not correlated with one another. We are collecting the sample from the population. So there, in this particular case, two types of correlation coefficients come into the picture. One correlation coefficient, which is telling you the correlation between the two variables taken from the population, that is called the hypothetical correlation coefficient, that will be hypothesized, and we do not have any idea about the actual idea about the correlation coefficient. We can only assume it. We shall call that correlation coefficient as population correlation coefficient. Population correlation coefficient means the two random variables, capital X and capital Y, that are associated with the population. What is the correlation coefficient between them? And when we are selecting the sample from the population, then we can calculate by our usual methods the sample correlation coefficient between the two variables. So in this particular case, two types of correlation coefficients will play. One is population correlation coefficient, and another is sample correlation coefficient. Okay, now we want to test the correlation coefficient of the population random variables, which will be hypothesized in the null hypothesis. Suppose my population correlation coefficient, I denote this population correlation coefficient by rho. So this population correlation coefficient will be having some value rho naught. Okay, or it is better to consider the population correlation coefficient to have no value, zero value. That means we also can assume that the population variables are not at all correlated. So if these are my hypothesis, this is my hypothesis. So what we actually do, we try to collect the sample from the population and we try to measure the sample correlation coefficient between the two, Rxy. Now, on the basis of the sample Rxy, let us call it as rho xy, or this is as rho xy. So on the basis of the sample sample correlation coefficient Rxy, I am going to reject or accept our population correlation the hypothesis related to population correlation coefficient. I shall stick to this particular null hypothesis. So in my problems, I will assume that the population population variables, random variables are not correlated at all. Okay, so we'll try to understand this particular problem on the basis of an example. So first of all, I'm going to give you an example. So here is a question for you. A random sample of 27 pairs of observation, 27 pairs of observations, 27 pairs of observations from a normal population, gave a correlation coefficient of 0.6. Okay, question is this significant of correlation, in the population? So this is the question. Okay, and so first of all, let us try to deal with this particular example. So it may so happen, you may think that if the population correlation coefficient, population random variables are correlated, obviously sample correlation coefficient, there must be some sample correlation coefficient. I mean, if the population variables, random variables are correlated, the sample will also show correlation. So, or you can say that if the sample is showing correlation, there must be some sort of correlation between the population random variables. Now, this is not always the case. You have to understand the situation properly. What sample is behaving, that will not validate that the population random variables will behave in a similar manner or so. Suppose let me set an example first of all. Suppose I have 10 students. I have collected a pair of 10 students, 10 boys and 10 girls. Okay, and this sample that I have chosen from population is a sample from the population of boys and girls who are students. Okay, so I have chosen 10 students each, for 10 boys and 10 girls who are BTech students, computer science engineering, and I have taken a test of, I have measured their IQs or on the basis of certain examination, certain topics. Okay, now suppose their IQs show a correlation coefficient, a high positive correlation coefficient. If I consider the IQ of the boys to be capital X and IQ of the girls to be capital Y, so the random variables X and Y are showing high positive correlation coefficient. Suppose it doesn't mean that if my sample of these boys and girls show high correlation coefficient on the basis of some subject on which they performed, doesn't mean that population of all boys and all the girls will do the similar, will show a similar kind of correlation. It is because suppose these 10 students, boys and girls, they take private coaching somewhere in some city, and I have collected those who are getting some extra facilities. So on the suppose this type of students have been collected in my sample. When I actually want to collect the sample, my sample needs to be random. students, it should contain all students who are taking the coaching, not taking the private coaching, started taking the private coaching and then left, and so on and so on. I have to take care all such possibilities. But here I have intentionally or unintentionally have taken into consideration only those who are getting extra facilities. Maybe this is the reason for which these random variables in my sample are showing high positive correlation. That doesn't mean that there will be high positive correlation between the IQs of boys and girls in the population. Okay, so this is one of the examples that I have cited. Now, according to this question, first of all, I need to set up my null hypothesis. So let's start this particular problem in the next page. So first of all, we set our null hypothesis as follows. We set H naught, and in null hypothesis, we are setting that the population correlation coefficient XY between XY is 0. That means there is no correlation. There is no correlation between X and Y in the population. So this is my null hypothesis. Okay, this is my null hypothesis. And in alternative hypothesis, I'll assume that there is population correlation coefficient. There is correlation coefficient between capital X and Y in the population. Okay, so population correlation coefficient is not 0. Now, to test the null hypothesis, the formula that we actually use over here is the following. So under H0, we use the t statistic as small t, small r is the sample correlation coefficient between random variable xy. This will be multiplied by under square root n minus 2. And here we'll write in the denominator 1 minus r square, which is the square of the population correlation coefficient. This sort of formula actually follows t distribution with n minus 2 degrees of freedom. Or we can write follows t distribution with n minus 2 degrees of freedom. Okay, so now we will try to find out what are the information that we have in our example. So first of all, you see that we have the information about the sample size, which is 27. So here n is 27. And correlation coefficient between the two variables is given to be 0.6. So they have already calculated the correlation coefficient between the variables. So this is my RXY. Also, one important thing is that in all these cases of t statistic, we shall assume that the population is behaving normally, or the population probability distribution is normal, because t distribution is a kind of distribution which behaves like normal distribution. So this is a very important assumption over here. And not only this, when you keep on increasing your sample size, by central limit theorem, we know that for large sample, the population always tends to behave like normal population. Okay. So we can substitute these values over here. So we have this 0.6, and this would be 27 minus 2. And in the denominator, we will write 0.6 whole square. Now I shall ask one of you to please calculate and send me the value by messaging directly in the chat box, and tell me what is the value of this t statistic. Give me the value of this t statistic. Any one of you can calculate this value, and the chat box is open. I have opened the chat box. So you can write in the chat box your value. Directly you can send me the message. What is the value of this T statistic? I think it's yeah. Okay. Got it. So the value is coming out as 3.75 approximately. It is coming as 3.75, and therefore now what you are going to do is that you are going to check this tabulated value, this calculated value with the tabulated value. Remember, if t comes out to be negative, we always take the modulus sign, but here t is positive, so you don't have to do it. If you go to the t distribution table, the tabulated value of t statistic, the tabulated value of t statistic is 2.06 at 27 minus 2, that is 25 degrees of freedom. And we see that the calculated t or you can say the mod t, calculated mod t is greater than tabulated small t at 5% level of significance. This value 2.06 is for 5% level of significance. Okay, so when the calculated t value is greater, then we actually reject our null hypothesis, and we conclude that the population correlation coefficient is not equal to 0. So there is some sort of correlation coefficient between the random variables associated with the population. Okay, the given problem has another part. A second part was also there. So let me write the second part of the question in the previous page. Okay, so the question was, we can call this part as 1. So the solution 1 has already been done. Solution the question 2 is, find the list value of R in a sample. Find the list value of R in a sample of 18 pairs of observations from a bivariate normal population at 5% level of significance. 5% level of significance. Okay, so we are going to find the least value of the correlation coefficient R in a sample of 18 pairs of observations from a bivariate normal population at 5% level of significance. Here you see, in this particular part of the question, the sample size has been changed to 18. So this is a kind of different problem. So sample size is 18, and the correlation coefficient, the sample correlation coefficient is actually not given. We want to estimate it. So how can I do this particular problem, this sort of problem? Let me explain in the next page, next to next page. So this is the question. Probably you have copied the question in your copy, and then I'm going to the third page to give you the solution. Here Just a minute. Okay, here solution. The sample size. Here the sample size is 18. This means there are 18 pairs of observations. That is 18 pairs of observations. 18 pairs of observations are there. 18 pairs of observations are there. Okay. And from table at 5% level of significance, at 5% level of significance for 18 minus 2, that is 16 degrees of freedom. 16 degrees of freedom. The value of t is 2.12. Okay. Now, under the null hypothesis, under H0, which is rho xy equal to 0, the t statistic, we already know that the t statistics is given to be r into n minus 2 divided by 1 minus r square. Here the correlation coefficient r is actually the correlation coefficient between the two variables x and y. And we know that this follows t distribution with n minus 2 degrees of freedom. Okay. Now, in order to calculate value of t, sorry, the statement is wrong. In order that, sorry, let me rectify the statement. This is not what I want to write. I want to write, in order that the calculated t is significant, at 5% level of significance, we must have this quantity r into 1 n minus 2 under square root by 1 minus r square under square root sign. Modulus of this quantity must be greater than t.05. Now, if I substitute the values, we know that this would be 18 minus 2 under square root by 1 minus r square under square root. Modulus of that must be greater than 2.12. If I simplify a little bit further, what will I get? We can square both the parts. We can get r square into 16. So r square into 16, and in the denominator we are getting 1 minus r square. 1 minus r square, that should be greater than 2.12 whole square. This will imply that 16 r square should be greater than 2.12 whole square into 1 minus r square. Now I want you to simplify this particular expression and tell me, if I want to write it in this form, that r square is greater than something, what can I write over here? What value will I write over here? simplify this particular inequality and tell me what will come in this particular uh, on the right hand side of this inequality. If I keep only r square on the left hand side, what will be there on the right hand side in this part? So simplify it and tell me the value. Meanwhile, you can put your attendance in the chat box, and the value that you are calculating, you can directly send me. You can send a direct message to me. Tell me the value here. R square is greater than something. What is that something? Give me that value. Yeah, got it. It is 0.2193. Okay. Now, if it is so, then if I calculate, if I take the square root of that, we will get modulus of r should be greater than 0.4682, I think. Just check. Am I right or wrong? If I write the square root, it should be 0.4682. If now you know that whenever x is greater than mod a, now from real analysis, we can write it as x is less than minus a or x is greater than plus a. If x is less than minus a, then also mod of x is greater than mod of a, isn't it? So this implies mod of x greater than mod of a implies this thing. So but if I want to apply this particular logic over here, we see that the correlation coefficient should be less than minus 468.4682, or it should be greater than 0.4682. So these are the limits of the correlation coefficient that we need to find out for these 18 pairs of observations that is given. This is the least value of r. Now, see, this particular limit is actually on the negative side, but it is not giving you the least value. If I consider the negative side only, and correlation coefficient must be, you know, the lower limit of the correlation coefficient is -1. Now, whenever if I consider this one, suppose I'm considering case 1 as r less than minus 0.4682, then we cannot say anything about the lower limit. We know that it should be -1. Okay, but it is not. It is kind of we are not sure about the lower limit here, so we shall not consider this part of the problem. Case 1 will not be considered because it is open-ended. Okay, but if I consider the case 2, there we see that r must be greater than 4682. That means you can write it as 4.4682. This should be less than r. So it is quite obvious that this is the least value of r. Okay, so 0.4682 is my answer. Approximately 0.4682 is my answer. So in this manner, you can take the help of this hypothesis testing to calculate the correlation coefficient between the two random variables to check whether there is any sort of correlation coefficient in the population or not. Let me give you another example. The example is like this: a coefficient of correlation, of 0.2 is derived from a random sample of 625 pairs of observations. Number one, is this value R significant? This is question number one. And question number two is, what are the 95% and 99% confidence limit to the correlation coefficient in the population. Okay, these are the two questions. And you see, one thing that I must mention, you are supposed to solve this problem by yourself. Okay, so before I join the next session, or even after I join the next session, then you are supposed to do this calculation and tell me the values, that what are the limits that you have got. Only one thing that I need to mention is that in this particular problem, you have to design the null hypothesis of the population correlation coefficient, just as I did in my previous case. You have to use the formula that is given to you. Now, question is, what about what you want to write about this standard error of R? What is the formula for that? Okay, so that thing I'm giving you the formula for the standard error of the population correlation coefficient, or 95% confidence limit. So 95% confidence limit, this formula is given to be, in this particular case, it would be the correlation coefficient R plus minus 1.96 standard error of the correlation coefficient, or you can write it as R plus minus 1.96 1 minus R square divided by root n. This is the formula that you are going to use. Why am I using this formula? Since your n is very large, it is a large sample, so we are going to use this formula. And 99% confidence limit will have the formula R plus minus 2.58 1 minus R square divided by root n. So with the help of this formula, you can calculate the correlation coefficient, confidence limit of the sample correlation coefficient. Confidence limit of the population correlation coefficient. That means your population correlation coefficient rho is going to be contained in these two values, like this, because we are going to estimate we are going to do some kind of interval estimation in case of population correlation coefficient. But if the population correlation coefficient comes out to be 0 with respect to your testing, then we don't have to find it out. So try to solve this problem by yourself. We are going to continue in the next session.